Hello, everybody. This is your examples / practice problems video for sampling distributions of proportions. Okay, I have 3 different examples for you. And this first one deals with this program on the calculators that I have in my classroom, where basically where the calculator will draw an ellipse and a rectangle around that ellipse, and then it will throw darts at the calculator screen, and then it will give you a proportion of darts that are inside the ellipse, and that's something that we can use to calculate the area of that shape without necessarily knowing all of the things that you need to know in order to calculate the area. Okay, so for the purposes of this problem, I'm going to tell you that the true proportions of dots that will land inside an ellipse for these specifications, where you have like this length here is 4, this length here is 3, right? So that true value is 0.785. Okay. Now, because this program runs randomly, it's not going to give us that true value every single time, right? So instead, it gives us sample proportions, right, that we can use to make a sampling distribution, okay? So we're going to do that, and we're not actually going to create the sampling distribution. I'm just going to tell you that it's possible to create the sampling distribution, and we're going to use that to find some probabilities. Okay, so the question here is, what's the probability that we get a sample proportion less than 0.75? Okay, so just as a reminder for you, the true population value is 0.785. That's the true population proportion. And I'll tell you that the sample size that we typically use when we run this program is 100, or 100 dots. Okay, so part A here says find the mean and standard deviation of the sampling distribution. Okay, well, okay, the mean, remember the mean of the sampling distribution, so mu of p hat is equal to the population proportion, which is 0.785. Okay, it's given to you in the problem. Don't make it more complicated than that. Okay, it really and truly is that simple. Okay, for standard deviation, you have to do a little bit more solving. So standard deviation of p hat is the square root of p times 1 minus p divided by n. Okay, so hold on, these are way too close together. There we go. So standard deviation would be 0.785 times 1 minus 0.785 divided by 100, all underneath the square root. And once you get to that point, just plug that sucker into your calculator. Okay, and when you do, or when I did, I got 0.0411. Okay, so my final answers for mean and standard deviation are here and here. Okay. So part B says to check your conditions. So remember, we have those 3 conditions that we have to check. The first one is randomness. Okay, and I'm going to tell you, right, that this is a random sample of points, right? That's how the program is run. Okay. Second condition is the independence condition, or you'll hear me call it the 10% condition. So is the populations of points larger than 10 times the sample? Well, yes, because there's an infinite number of points. Okay. Okay, but if you want a like word formula, in order to show that this is true, what you would do is you would take the sample size times 10. So you would do 10 times the sample size, figure out what that is. So in this case, that's 1,000. And we would say that is less than the total number of possible points. Okay, so this right here is like a formula that you can use that will work for just about any scenario. You just have to make sure you include the correct context here. Okay, so remember, it's 10 times your sample size, which is n. Okay, and then the last condition I have to check is here I said large enough sample, but remember this is your success-fail condition. Okay, so where we have to check the number of failures and the number of successes. Okay, so number of successes is n times p, which is 100 times 0.785, which is 78.5, and that is greater than 10. Okay, so I can say check, right, for number of successes, and then I have to do the same thing. Whoops, didn't change my color back. Whoops. I have to do the same thing for number of failures. Okay, so that's n times 1 minus p. So 100 times 1 minus 0.785, which is 21.5, which is greater than 10. Okay, so check, right? So I've checked my 3 conditions, so I'm all set, right? Remember, the point of all of this, the point of checking conditions is to see if we can use our normal distribution tools. So because all of the conditions were met, I can use my normal distribution tools, which is awesome, okay? So now we're going to get back into exactly what you did in Unit 3, right? Because I have a mean and a standard deviation, and I have a data point, right? So you may have been thinking, wait, where did that 0.75 go? We haven't used that yet. Okay, that 0.75 is your data point. Okay, so if I wanted to draw a picture illustrating this probability, okay, I'm going to draw my normal distribution. Hold on, let me move this guy up just a little bit. Okay, I need to draw my normal distribution, right? Sketch it out, right? So I need to draw my mean, which was 0.785. Put my standard deviation up here at the top, which was 0.0411. Okay, and then my x value, right, or my data point is 0.75, which is about right here. Right, remember, it's approximate. You don't have to be exact. Okay, and what we are trying to find is the probability that we get a sample proportion less than 0.75. So I'm going to shade to the left, okay? Which I'm going to show you again here on the left side of your screen. So remember, this sketch here, all of these individual data points are p hat values, right? They're not counts, they're proportions, okay? Right? So now the last part of this is, okay, now that I've sketched my distribution, I need to find my z-score and use either the z-table or a calculator in order to figure out my probability, okay? So what we're actually doing is we're saying z is the sample proportion value, p hat, minus the mean of p hat divided by the standard deviation of p hat, okay, which looks a little bit more complicated, but it's the exact same formula that you're used to using. Okay, remember the z-score formula that you know from Unit 3 is x minus mean divided by standard deviation, right? Data point minus mean divided by standard deviation. It's exactly the same thing here, okay? So I'm going to do z equals 0.75 minus 0.785 divided by 0.0411. Okay, so my z value is 0. Let me see, I calculated it for you here. Oh, it's negative. Apologies, I forgot my negative sign. So negative 0.852. Okay, remember that's not your probability, that's your z-score, right? So what we're actually trying to find here is the probability that p hat is less than 0.75. That's the same thing as the probability that z is less than negative 0.852. And like I said, you can either use the z table to figure that out. Whoops, I went too far there. Or I used my calculator, right? So I used the norm CDF. And when I did, I got 0.197. Okay, so remember, you can use a z table to figure out that probability. If you're going to use a calculator, your command is normal or norm CDF. Okay, so the answer to this question, what's the probability that we get a sample proportion less than 0.75, that probability is around 20%, 19.7%. Okay? All right. Let's look at a slightly different example. Okay? So here's another example for you. I have the Gallup poll asked a random sample of 100 adults. Okay, so good idea to label as I go. So 100 adults, that's N. Okay, so they asked, do you jog? It says, suppose in fact 8% of all American adults jog. Okay, so 8% is the true population proportion, or lowercase p. Okay, this says find the mean and standard deviation, and then find the probability that between 13 and 17% of the sample jog. So these right here would be your p hat values, okay? Those are like your data points that you're focusing in on, okay? So let's go ahead and use our formulas to find the mean and standard deviation. Remember, mean is very simple. The mean of p hat is just the true population proportion. So it's 8%. Typically, you want to write these as decimal values rather than writing them as percentages. Okay, standard deviation is a little bit more complex. Okay, so it's the square root of p, 0.08, times 1 minus p, so 1 minus 0.08, divided by the sample size, 100, all under the square root. Plug that sucker into your calculator, and you get 0.02. Oops, that 0 looks crazy. Let's try that again. 0.0271, right? You may have gotten something slightly different than me if you rounded at some point or rounded a little bit differently, but there's your mean and standard deviation, okay? Part B says, check conditions, draw a picture, and find the probability if possible. Considering the fact that I did not give you a bunch of space, I'm hoping that a slight little red flag is going off in your brain, which says that maybe one of these conditions is not going to fly. Okay, so my first condition is randomness. Okay, and so you just have to look back at the problem and say, is this a random sample? Okay, all you have to do is say simple random sample stated in problem. Okay, that's it. Okay, 10% condition, right? Remember, we do the sample size times 10, so 10 times the sample size, which is 100. Figure out what that is, which is 1,000, and I'm going to say, yeah, that's less than the total number of American adults. Okay, frankly, there are more than 1,000 American adults who are parents at Valley High School, right? So there's your 10% condition. You can also just state, like, it's reasonable to assume that there are more than 1,000 American adults, right? But this little formula will work for you every single time, okay? And then the last thing we have to check is the success-fail condition, which you'll see me abbreviate as S-F, right? I called it large enough sample here, but most of the time we call it success-fail. Okay, so I have to check number of successes, number of failures. So NP is the number of successes, right? So NP has to be greater than or equal to 10, right? That's what I'm finding. Okay, so N is 100, and you can obviously see this on the left side of the screen here. N is 100, and probability P is 0.08. Okay, so that is 8, right? Which is less than 10. Okay, so this condition failed, right? So success-fail condition not met. Okay, so this means we can't be certain the sampling distribution is normal. Okay, there's no way for us to know for sure. Go like this. Okay, you can't continue the problem after that, right? We can't be certain that the sampling distribution is normal, so you have to stop the problem right there. Okay. All right, you guys. So there's one more full problem, like full example problem here that I want to see if you can do on your own. Okay, so this is typically the order that we do these problems in. So before you do anything, check the 3 conditions, then calculate mean and standard deviation, then do all of your normal curve stuff. So sketch the curve, calculate your z-score, and find your probability, either using the z-table or using your calculator, right? And then this one has a binomial component. I want you to see if you can calculate the probability here for this, not using a sampling distribution, but using the binomial distribution instead, and see what happens, right? So go ahead, pause the video, and then check back with me in just a sec to see how you did. All right, folks, so go ahead and take a look at the fully worked out problem on the right side of the screen, and I'm going to talk you through it and kind of work through it here on the left side of the screen. Okay, so the first question you want to ask yourself whenever you're dealing with a sampling distribution problem is this data categorical or quantitative? This data is categorical. Either a car exceeds the speed limit or does not exceed the speed limit. Okay, so that means if it is categorical, you're dealing with proportions, right? And obviously, because this section is on proportions, right? But when the problems are mixed with means, it's a little bit harder to figure out. Okay, so before I do anything, I have to check my 3 conditions. Okay, so my randomness condition, it said in the problem that I was dealing with a random sample, so I'm good there. My 10% condition, 10 times 50 is 500, which is a reasonable number for a sample, right? That's got to be less than the total number of cars that travel on the interstate. Okay, and then the success fail condition also checks out, right? Number of successes, 50 times 0.8, which is my 80% is my population proportion, right? It said of all cars on the interstate, 80% exceed speed limit, right? And then they gave me my sample size was 50. Okay, so 50 times 0.8 is 40, which is greater than or equal to 10. And then number of failures, 50 times 0.2, which is 1 minus 0.8, is 10, which is greater than or equal to 10. So I just barely squeaked by there. Okay, but I'm good on all conditions. Okay, so next, calculate the mean and standard deviation. Okay, so the mean is just the same as the sample, not the sample proportion, sorry, the same as the population proportion, 0.8, and then I use my formula to calculate my standard deviation, and I got 0.0566. Okay. So here's a sketch of the normal curve. Yours does not have to be as detailed as mine, the way it is on the left side of the screen. Yours probably looks a little bit more like what I have on the right side of the screen. Now, you may have looked at this problem and said, but where's the sample value? Like, where's the sample proportion? They did not give this one to you as a sample proportion. They gave it to you as a number of successes, right? So we're finding the probability that a random sample of 50 cars has more than 32 of those cars exceeding the speed limit. So that's the number of successes. 32 is the number of successes. So the population proportion is 0.8. The sample proportion is the number of successes, x, divided by n, the sample size. So 32 divided by 50, which is 0.64. Okay, so I sketched my curve, shaded it in, and I'm trying to find a more than probability, right? A more than 32. So I shaded to the right on my normal curve. Okay, so now I have my p hat value, which is my data point, right? So it's like my x in the z-score, my mean for the sampling distribution, and my standard deviation for the sampling distribution. So I plugged those into my z-score, and I got negative 2.827. So, and even just looking at the diagram, you can probably tell that this probability is going to be pretty large, okay? So I am finding here the probability that p hat is greater than 0.64, okay? Which is the same as 1 minus the probability that it's less than 0.64. Because if you recall, on the z table is always going to give you left probabilities, like left shade probabilities, or less than probabilities. If you used your calculator, you didn't necessarily have to do the 1 minus thing that I did here. I just wanted to do it as an example for you to remind you of that fact if you're dealing with the z table. Okay, so the number that I got for the less than probability is 0.00235. So 1 minus that value is 99.765%. Pretty high. Okay, so that is my probability. Okay. Now, in the last unit, we used a binomial distribution to solve problems like this. Okay, so here, right, this is an example, right, of how you would do this with binomial, right? So rather than figuring out the sample proportion, you would do the binomial conditions, you check your binomial conditions, and then you would calculate your binomial probability, which is the probability that x, the number of successes, is greater than 32. So you'd have to find the probability of each of those x values that's greater than 32. So probability that x is 33, which is the one that I have written out for you, then plus 34, 35, 36, all the way up to 50, right? So remember, you have your number of arrangements, right? So this is 50, choose 33, successes, probability of success, number of successes, probability of failure, number of failures, and then you or your calculator would have to repeat this for all of the values greater than 32, but less than or equal to 50, right? Which is kind of a pain, but when you do, you get 0.99749. So incredibly close to the probability that you get with the sampling distribution, okay? But I would argue that it's much more difficult and much more like strenuous to calculate the binomial probability than it is to calculate the sampling distribution probability, right? Because you're just dealing really with a z-score when you're dealing with the sampling distribution probability. All right, folks, that is it for this video. I hope that you found this informative and helpful, especially to see these problems worked out. If you follow these steps, no matter what, in any problems dealing with sampling distributions of proportions, you'll be able to get to the correct probability. All right, you guys, I'll see you in the next section where we're going to do a very similar thing, just with sampling distribution of means. So I'll see you in the next one. Bye, everybody.